Recording this computer. Okay, good morning, everybody. It's April 22nd. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Everybody's here except Aaron, who is on the beach, right? Enjoying family time. So hopefully he'll get to watch these recordings before we get rolling too much further. So for this first 20 minutes or so, I want to show you my final expectation for this Excel project. A couple of you have not submitted anything, which really worries me that I've completely left you flat-footed, or you're actually working during the class and they're not giving you any time to practice this stuff, which is equally worrisome for me. So I'm going to show you where I want you to get to be done with this little exercise. Okay. So from the Excel standpoint, some of you have a whole bunch of data. Um, so what I want you to get to is, let me share my screen so you can see what I'm talking about. There we go. Okay, I was up at 4 a.m. Got to sleep pretty early, about 4 o'clock. I'm like, boo! So much to do. It's the end of the semester for a couple of colleges I teach for, and we got this class going on. Okay, so what I want you to get to is I would like for you to submit 2 files. One being your basically your clean data, which for me is like my all data tab. Get over there. There we go. Okay, everybody can see that, right? Okay, I was dorking around with a few different things, just really having a blast with Excel. I mean, if you're bored and you need something fun to do, just open Excel and just start playing around. So I decided that I had to get real and limit this down, just like I would like you guys to just choose something very simple so that we can complete this exercise. I decided to look at temperature, average daily temperature, and happiness. And I put population in there for you, plus the little abbreviations, just to kind of as that data wrangling exercise. But so I looked at average temp and against happiness, and did a little bit of analysis as far as winter temperatures and their effect on this subjective rating of happiness that I told you guys about before. So so I would like to see this clean data sheet for whatever you're doing. It doesn't really need to have any extraneous data. What I've got here simple is fine. So kind of take some pressure off yourself, clean it up, and get it down to the data that you need to address this question. And then I used Excel to take just my important data. The less data you have in a worksheet, the less confused Excel will get, and the less complex things happen. So I brought my state abbreviation over here, and my temperature and my happiness score. And this is the average daily temperature in winter. And I did I inserted a recommended chart, and it was a scatter plot. Now, when you first do that, for whatever reason, it doesn't give you X and Y values. And I did a little bit of reading. You want to put your X, your independent variable, in the first column, and your dependent variable in the second column, to avoid having to do editing, and it gets a little confusing if you try and swap the X and the Y after you draw the chart. So I drew those, and then see this plus sign in the upper right corner here and chart elements. If you click on that, you can add axis titles. And so I added temp as the independent variable and happiness as the independent variable because I'm thinking, average temperatures affect happiness. Happiness doesn't affect the weather, right? The weather doesn't know if you're happy or not. But if you're happy and you know it, clap your hands. Oh, come on. That was a good one. I got a smile. I think that was really more of a cringe than a smile, but I appreciate it. Anyway, so I drew this and then in order to add the trend line, you right click on any data point and say add trend line. And I also added the you'll get a dialog box. I've already got it up there, so it's not popping up. But you add the trend line, and then you can choose to add the equation. Like if you were going to do, some linear regression and say, okay, well, gosh, if global warming happened, what would be the effect on happiness? Because then you've got the equation that you can project a change in average winter highs. And then you've got this R squared value, which is always positive because if it's a negative R value and you square it, you'll get a positive. So I ran my numbers, right? I got two variables. They're not categorical; they're numeric or continuous variables. And I created a simple chart and found my statistics. But I also went in there and ran with my data analysis pack. Let me go back and do that one for you. You click anywhere in your data, and you say on the data tab, you click on data up here on that tab, and then you click data analysis. Something I was doing wrong and getting that error was the way I was choosing my columns to be correlated. So I want to find a measure of correlation. So I choose correlation and I say, okay. And then remember labels in first row always. But when you're choosing your columns, I was hitting control. So if I backspace over that, I was hitting control, but you want to hit shift. So the first column I want in my input range is temperature. And then you go over to C and you press shift and it sticks in all of B to all of C is what that $B $C means. All of B and all of C. That's my input range for this correlation statistic. And remember labels in first row, and then you say okay. And I had it in sheet 3, just reran it for sheet 4. But our Pearson's R correlation coefficient is negative 0.14, which it showed in my graph. Negatively correlated, but very, very weakly correlated. So my research hypothesis that sunny, warm temperatures make you happy, apparently the underlying data of that happiness research didn't ask about it, didn't care, or it didn't matter. There's a whole nother methodology section to examine and how you got your data for something like a happiness score. Beg your pardon. It was cold this morning. I had to put on a jacket to let my dog outside. So yeah, Pearson's R is that statistical measure of how they correlate, and your chart shows that perfectly. It's a really weak line. If you had a 45-degree angle line, that's pretty much perfect correlation. 45 negative or 45 positive. So that's my R value, and that's how you run that. So that's what I would like to see from you guys. You don't. Yeah, it'd be good to leave it in the sheet, using whatever statistical test you're using. And if you need help with that, let me know, and I'd love to dig into it with you. If you're doing a categorical against a numeric, I think we got to do chi-squared or something, a different test. But actually, now that I'm thinking about it, it should choose when you choose correlation and come up with a score. But then we got to dig into exactly what Excel is doing by magic. So anyway, that's what I'd like to see. a spreadsheet, a nice clean spreadsheet, so I can see that you're cutting and pasting columns and you got that down and you're okay. No formatting, no nothing, just headers for your data. Okay, and then I'd like to see your just the columns that you need, just the columns that you're using, and your graph. Now that if that's one chart or two, I'm encouraging you to limit this down and get to one or two little questions, just that we can stop having this hanging out as kind of an intimidating thing. I think for some folks, there's just uh, uh, too many questions, too much data, and you just got to kind of go ahead and just decide something simple. So anyway, yeah, and then your statistical analysis sheet, whatever you're doing. So I really only need 3 sheets: all your data, your chart, and your stats. And I'll create a new assignment for this and call it a final states project, and I'll put it in the description of the assignment. And then we got 13 more minutes. And then the next file I'd like you to upload is, now come on, what did I do with it? I put it in the Excel file. Okay, let me unshare. Stop sharing that. And the next thing is a very short presentation to walk through what you did. Come on now. There it is. And I'll post this in Canvas for you to use. But it's a PowerPoint, of course. You don't have to use PowerPoint if you want to use Word or something like that to tell your story. That's what we're getting at. Remember the data analysis process from start to finish: research question, gathering data, analyzing the data, reporting the results. Remember that was the whole point of this exercise, is to do one with very, very limited scope, just to get it all in our heads. So let me share my PowerPoint. So I ginned this up this morning. Here's my research project. So do a slide on what's your question. Like Thomas was looking at fatalities associated with helmet laws in states. There was another one looking at employment rates and suicide. I downloaded everybody's spreadsheet and took a look. Everybody that uploaded one. A lot of good stuff in there. Just need to narrow that down to something definitive. So my question was, what relationship? And remember what you're asking. What relationship does a state's daily temperature have on a happiness score? And that, that opens up all kinds of questions. Lots of other factors affect happiness, right? So it's really hard. It's really hard to pin down cause and effect, but you can look at the math. You can look at the no kidding, the correlation between two variables. So I looked at, what's the relationship between those two variables. And as we talked about with Dr. Aguirre's presentation on Tuesday, my null hypothesis is nothing to see here. That's always your null hypothesis when you're reading anything about a study or research data. The null hypothesis is that there's no effect, there's no relationship, there's nothing to see here. That's why they call it the null hypothesis. But then you always see alternate hypotheses, and you can have more than one. So I had 2. My alternate hypothesis is that there is a positive correlation between temp and happiness. As your winter temperature is warmer, people are naturally happier. That was my alternate hypothesis. Alternate hypothesis 2, though, is the opposite of that there is a negative correlation between temp and happiness. Then your next slide will be just to talk about where you got your data. You'll always want, as an analyst, you will always need to be able to tell people where you got your data. You put up anything that's even close to controversial or going to be used to make a decision, they're going to want to know where you got your data and how you did your calculations. So make sure everything is as transparent as possible. So there's my sources of my data, and that happiness score. If you want to check that out, it had a whole lot of factors. So I showed you guys that. So anyway, and then your next slide will be your analysis. And here's that chart that I showed you in Excel. Just save it as an image, blow it up, stick it on your PowerPoint. I added a text box here that shows my R value, and R squared is literally just that squared, to show the negative. The R squared shows the strength, but R will tell you if it's negative or positive. That's another question I'm going to ask Whitney. If none of you do. Why do we have R and R squared? Why not R cubed? Why not R Kelly, for all I know? Thank you, Laura. I saw you smile. I appreciate it. I write these jokes, guys. I take hours before class to write these jokes. And
I know that I'd admit that, Don.
You didn't get R. Kelly?
Oh, I got it.
Okay. Yeah. I just didn't see any humor in it. I got it. I'm trying here. I get no respect. So that's when I'm going to start to roll. I mean, it's Googleable. We could all learn every question we could possibly ask her, but it would be good to see her description. 8 more minutes. So check out Hawaii up here. This outlier up here. Let me go back to my spreadsheet. Short attention span. Finish what I'm doing. Your last slide. What are your findings? Your last slide in your PowerPoint. So I kind of did a little bit of background. What is our measure here? Our data shows negative 0.14, which -1 would be perfectly correlated. Negative 0.5 is getting to be significantly correlated. Generally speaking, anything of R that's between negative 0.5 and 0.5 is not really a significant enough correlation to draw a conclusion. So as a researcher, my recommendation is to accept the null hypothesis that they are not correlated, which I did a little other Googling, and yeah, like Scandinavia, they're as happy as they can be. And it's cold there. But then Hawaiians are happy and it's warm there. So there's other factors at play. And that's all that's all this is just an exercise looking at a couple of variables without necessarily drawing any causation. You know what I mean? You don't know any cause. You just know, predictors and results. And that's only if you're doing very specific measures, very specific. So that was mine. That was just looking at a value or just looking at the data that you have on hand. Questions? Any questions on that assignment? We got 6 more minutes. Any questions on that assignment? What I'm looking for? I'll post both spreadsheets and PowerPoint up there, but I'll be looking for 2 files. And I'll give you time this afternoon and Thursday to wrap this up. Like I said, a couple of you I haven't seen anything yet, so that really has me a little bit concerned. So contact me if you don't want to come off mute and talk to me, talk to us as a group. Please certainly email me. We can get together on Zoom separately, or I'll call you back. If you text me, I'll call you back. Chase wanted to know about swapping the X and the Y, which is complicated. There's if you Google it, it shows you how you do the you right click on the axis and you have to swap the values in a dialog box, and I couldn't get it to work. So that's why I recommend cleaning up your data and putting it in the order that Excel is expecting it to be. for a scatter plot. No questions?
Don, I was going to ask you, you are going to post this PowerPoint on Canvas, right?
I certainly will.
Okay.
In fact, close that window. I'll do that while we're waiting on. If you got to take 3 or 4, this would be a chance to do it. I will post that right now. In fact, I'll post it and my V2 happiness spreadsheet. I'm trying to remember if it bings or beeps or when Whitney comes in. Certainly it'll give me an audible signal if I'm not looking at my window. So I think I could attach both of these to the assignment, but I'll upload them separately. Okay, slide that up a little bit. So you've got my initial one, which is kind of just the blank with population, and then project V2 that has the happiness and temperature in it. Indent. And then the slides. Brittany couldn't make it.
I'm gonna have to tell my lawn people to not come on Tuesdays and Thursdays.
It happens.
I was gonna ask, if you get the chance, would you mind clarifying what the alternate hypothesis is? Like, is that just something that you come up with, or is there a calculation?
No, that's a good a good question. It's It depends on what you're doing, and and I know this. It's not like I work in a lab and conduct experiments, so I don't develop these. But when you're reading the academic journal articles, if it's a quantitative research project where they collect the data and reported on the results, you always see this. The null hypothesis is nothing's happening here. It could be like a drug trial where your null hypothesis would be there's no difference between the treatment group and the placebo group in whether it's weight loss or decreasing blood pressure, decreasing cholesterol, whatever the case may be. There's no difference between those two groups. And then there's the alternate hypothesis is that the treatment group, there's Dr. Worley. The treatment group has a statistically significant increase, or decrease in cholesterol or decrease in blood pressure, whatever the case may be. But that's where that's one of my questions. Good morning, Dr. Worley.
Hi, I'm so sorry. My desktop won't even load my calendar. I have no idea. So we're using my personal laptop.
Okay.
Camera's not as good, but.
Okay. Well, welcome to another group. Whitney, you helped me out last year and actually taught some sessions. But I understand you've got some good news this year.
Yeah, we're waiting on a baby. Hi, Chase. Chase and I went to college together.
Oh my God. Hi, Whitney.
There you go.
Oh my God. That face is familiar. How crazy is that?
I'm shocked right now. How you doing?
Yeah, you probably didn't know my married name.
No, I sure didn't.
Well, that's right. I forgot your maiden name.
Burrow.
Ah, there you go.
Yeah, we're Wonder Boys. We went to Tech, so
Yeah.
Wonder Twin Powers activate. Huh?
Yeah. We used to hang out a lot too. I was in college. I dated one of his fraternity brothers, so we were around each other a lot.
Wow, this could have turned out really differently. Y'all could be exes or something. It'd be like.
No, that's just hilarious. I just looked down. I was like, I know that face, and then I saw your name.
There you go.
Yeah. Good to see you.
You too.
All right. Any other reunions? Unexpected reunions here? That's
not that I see.
That's awesome. All right. So yeah, another data analysis apprenticeship cohort, and folks are again coming in with varied backgrounds in analysis. Some just getting into it. They've got domain expertise in maybe marketing or curriculum development or healthcare or IT, but they're getting into analytics. And then other folks have various levels of education on the subject. So we've got the same variation in depth of experience and depth of knowledge in stats and analysis, and the breadth in domains. So just like last time, I had to muddle through without you this time. We did descriptive stats, univariate descriptive stats, so they kind of get an idea of that and what charts kind of show that sort of stuff. And we talked a little bit about bivariate analysis and the relationship between categorical variables, two categorical variables, two continuous variables, a categorical and a continuous. But it was very cursory. I'm an IT guy. I'm not an analyst or especially a mathematician. And then I had a colleague from Northwest Arkansas come in and do a little bit about experimental design. So they kind of have an idea what a null hypothesis is versus alternate. And we talk about accepting and rejecting
right
the hypothesis. But that's kind of where we left it off as far as any depth of I mean, we talked about p-values, but we didn't, didn't use it, didn't go into depth with it. So we've talked about statistics, but we haven't. I mean, this certainly isn't a statistics refresher, and no one had to have stats to get in here.
Right.
So based on what limited, I've been able to cover as far as, what we're looking at when it comes to numbers, when it comes to data. I'm sure folks I've got 3 or 4, but I'll defer to the students here. Whitney, before you accept questions, was there anything you wanted to accentuate or?
Honestly, I think it'd probably be better if I kind of see what they want to know and then go from there.
Cool.
And then I can also, if you want, I know you said you had one of my lessons recorded. I can also send you the PDFs for those slides. I have the intro to R, the inference, and the probability all.
Cool.
And I just went back and checked. I have a Coding Academy folder, so they're all still saved.
Yeah,
So
great.
if you would
could
like
send me
those,
that.
y'all can have access to that and use them as a tool if you would like that.
Sure. And I have your probability lecture recorded, but for some reason I didn't. You did 2. You did inference. I think you
I
did
did-
probability first and then inference. Is that?
I did probability and inference, and I did one on R programming.
Yeah, I've got your R. That's a great workshop. I've used that several times. That's a great workshop. But yeah, the inference and probability PDFs and your R workshop PDF, that would all be great information.
Okay, I can definitely send that over when we're done.
Okay. Questions from the field.
I do have a question, actually. Sorry about the noise in the background.
You're okay.
What is considered a quote good sample size?
That depends on the problem. There's a whole field of statistics for sample size determination. So it really depends on the problem and what question you're trying to solve on, if your sample size is big enough, and how rare the data is. So if it's something that's really hard to come by, sometimes especially when we're dealing with things like rare cancers, most of the time we can't get a very large sample size. So we have to just work with what we have. That's actually what part of my research is dealing with small sample sizes when we have a lot of data on a subject. So a lot of my research is in genetics, where we deal with really, really small sample sizes and hundreds of genetic markers for cancer patients. It's honestly, the good thing is the more data you can get, the better. But we all know that there's an amount of data that you can get that's feasible, right? So the time it takes to collect that data and the money that it takes to collect that data. So there are some basic things that you can do to guarantee, say you're trying to estimate a parameter, maybe a mean. You can in advance say, okay, I know that I want to make sure I'm at least this accurate. So those are some basic sample size determination problems. And you can put in some basic parameters and it will spit back, whatever program you use can actually return to you what a minimum sample size is that you need. A lot of times, if you're doing problems like that, you end up with something in the realm of 200 to 300 for depending on how accurate you want to be. But we know in the real world that's not always the case. I always say, especially when I'm showing my students bivariate data and we're trying to fit models and things, samples of size 10 obviously are not going to cut it. So it really just depends on the problem, but more is always better if you can get it. But
so when you're presenting your data, would you want to include the percentage of accuracy based on some sort of formula like that?
Anytime you present a result with an estimate, we never just want to present a point estimate. So if I have a sample of, let's say, 50 people, and I'm trying to calculate some mean value on that sample of 50, I'm not just going to report their sample mean. I'm going to also calculate a confidence interval so that I can say, not only is this the estimate I'm giving? I'm going to give a range around it that I think is feasible, that's based in probability. And that's where confidence intervals come from, or from the central limit theorem. And they give us a range of values and a level of confidence about that decision, so that we can say, okay, I'm 95% certain that I caught this number and it's between here and here. And that allows us to give not just a single number, but a range of possible values that are more feasible. You never want to print out a single number. Point estimates are great places to start, but they're terrible places to finish.
Is there a formula for calculating that?
Yeah, there are, and I think some of them are actually in my slides that I'll send you. And there's
Awesome.
every program, every basic statistics program has a way for calculating confidence intervals. Even in Excel, you can get free extensions for Excel where you put in your basic data and it will spit that information back out. And I don't know if the information for how to do that's in my R slides, but you can use R for that. You can use SPSS for that. And all you have to do is either give it the raw data or give it the summary statistics for that data. So the sample mean and the sample standard deviation, and it'll spit the range of values back out depending on how confident you want to be. So I know that there is some information about that in my inference slides.
Awesome. Thank you
But
so much.
that's, yeah.
Hey, Dr. Worley, it's Chase.
Hi, Chase.
Just a quick general question for
Mhm.
Don. Kind of highlighted that everyone here has different levels of statistical, knowledge. I'm one of the people that kind of need to start from scratch.
Yeah.
So he's recommended a college course. If we were just kind of trying to find a place online to practice like standard deviation and that type of thing, do you have any recommendations on how to do that on your own? Or
I will say one of my favorite places to start if you feel like you're starting from scratch is at Khan Academy.
okay.
So it's KHAN. They have instructional videos on understanding things, ways to calculate stuff. There is like an excellent online free tutor that I suggest to all my students. So it's a great place to start for like intro stat. And I'm going to go ahead and plug something, even though it doesn't quite exist yet. We are actually in the process of developing our own program for students who don't have a real stat background. It's going to be a graduate certificate that can be completed in a year. And we're in the process of developing that right now. So we're trying to build up some materials for that. And hopefully we'll have that ready by fall 22. So any of y'all get really interested in this, feel free to come back and see me and take my classes. But that's a great place to start, just like on the intro stuff. And then there's a lot of other resources online, but that one's one of my favorites just because it's not only practice, but it's also like video instruction with practice problems, and some different information like on, sometimes it's like how to do it by hand, and sometimes they'll give you information on technology that you can use. I will say the biggest suggestion I can give you, if you go back and look at like any intro text or anything like that, don't try to do them with the TI-84 calculator. Use a computer. That's where everybody's going. Use your computer. There are free programs online that you can use. There is free extensions you can get for Excel. There's more in-depth paid extensions you can get for Excel. Don't try to do it on a handheld calculator because it takes way too long to type all your data in.
Okay.
Andra had asked a question about developing your alternate hypothesis. We went over the null is, nothing to see here, no relationship, no before, after, nothing. But how do you develop Andra, go ahead.
I was really just curious about like clarifying how you come up with that. Is that something you come up with? Is there a formula for that or what?
It just depends on the question you're asking. So if we're dealing with numeric data, we tend to want to ask ourselves, first off, do I care about direction? So sometimes if you're dealing with, like, say, a business problem, you may care that your mean, let's say we're dealing with assembly times, okay? So my assembly time before I put in this new system was this. I know what it was because I was able to measure it on a daily basis. So then I'm going to sample the assembly time for 20 products, whatever it is. And then I'm going to look at those and I want to see, has my assembly time gone down now that I've put in this new system? Okay. If it's gone up, I obviously don't want the system. If it's the same, I don't want the new system because I'm going to have to install it at all my factories. It's going to cost me money. So I only care if it's gone down. So then I decide, okay, then my alternative hypothesis in that case is that it's decreased, right? If, let's say we're talking about students' test scores and we're going to try out a new ACT prep class, then I'm only interested in, is what I'm doing now better than what I was doing before? Again, because it costs me time, it costs me money to implement something new. So in that case, I'm only going to test a greater than alternative because the only reason I'm actually going to do anything about what, or change what I'm doing is because there's an increase in scores. And then there's other times that we don't really care about direction. And if we don't, then we do that. Those are the cases in which we do a not equal to alternative hypothesis, where it's just things have changed and we just need to know that they've changed. We don't care which direction they've changed. And then a lot of times in those cases, what happens is once we discover a change has happened, then we'll do that confidence interval calculation to see, okay, not only has it changed, but this is where that value is now versus where it was in the past. And a lot of times that's when we do those not equal to alternative hypotheses, we're looking at like past versus present. And we're just looking for a change in either direction. But typically when you pose a hypothesis, if there's a direction that makes sense, you use that in the alternative. You don't just default to not equal to, which is what some people do, and it's really not best practice.
Okay, I think I understand.
And then there are other types of hypothesis tests. So like one thing I'm teaching right now with one of my classes is analyzing categorical data. And so one thing that they talk about is in those cases, you get a null hypothesis of these two categorical variables are independent. They don't affect one another. The alternative is they are related to one another in some form or fashion. So depending on the problem type, for anything that's just like a straight numeric type answer, or like you're testing a parameter, you're always going to have a not equal to, a less than, or a greater than. Don't let anybody fool you into putting the equal to signs in those. That's really bad practice because it doesn't actually contradict your null hypothesis of things are equal. But then when you start talking about more complicated hypothesis testing, like for categorical analysis, then the null is always like no change or no effect. And the alternative is there is a change, there is an effect, and you have to kind of think about it in terms of the problem. Excuse me, sorry, baby gives me hiccups. You have to kind of think about it in terms of things are related, things are having an effect. So like we even use that in regression when we're wanting to see like, does the slope actually mean anything in a straight line model? Because if it doesn't, then my X is not telling me anything. So you can continue that idea beyond just like a single number and expand it out. But the null is always, there's nothing going on. The alternative is there is something going on, and you kind of have to just relate it to what hypothesis you want to pose.
Okay, so I think what wasn't making sense to me is how can you have a null hypothesis but still have an alternative? But I guess what I'm hearing is that you can still have a correlation, it's just not strong enough to be more than a null.
Exactly. Okay. So here's a way to think about that. So I may have a mean that's exactly 50, right? And or that's what's proposed in the null hypothesis. The mean is exactly 50. Well, we know when we deal with data that things are random, right? So if I take this 25 people, they're going to have a different sample mean than this 25 people, right? Because of randomness. People are different, individuals are different, so I'm going to get a different result from each one of my different samples. The real question we're posing is my sample mean, if this is my population mean, is my sample mean far enough away to say that it is truly different? Or is it close enough that the randomness is explaining that difference?
Okay.
And so when we reject, we're saying it's far enough away that there's no way that this number makes sense. This had to be a lie. The real mean is somewhere over here.
Okay, yeah, that makes sense. Thank you.
Do you guys mind if I piggyback on that? Because this is the perfect opportunity to clear something up and hopefully I didn't confuse the issue. Whitney, so when you're doing a sample of the population, I totally get it. And I think we all see that, you take people if you take a tiny sample, there's a chance that you ran into, outliers in the population. But the larger you sample, the more likely it's representative of the population. So I think we all got that okay. So what I used for an example this morning was assuming that you had data from the entire population for two numeric variables. Say you were able to ask every American, how happy are you? And then you're able to sample actually sample the temperature that they live in their state. So I had 50 rows. I'd buy 50 rows, and then I had a average daily temperature column and an average happiness rating from 0 to 100. So similar scales. My null hypothesis was that the temperature you live in winter has nothing to do with your happiness, how happy you are. That was my null. They're not related. And so I looked at drew it up and ran the numbers, and they are very weakly negatively correlated. But there's no confidence interval. There's no p-value. There's no, you know what I mean? So
the way that you can do that is you can fit a regression model and actually look at, actually test to see if that correlation or that slope in that case is actually giving you information. So you would test that slope to see if it's statistically different from 0. Because a weak correlation says that your slope, you may end up with a negative slope, but it may just be based on the randomness in the data rather than the actual relationship from between the two variables. So
I need more training.
that's just one way to check it. That's one of the easiest ways to check it. So anytime, and this is the way I tell my students, like if you're going to try to fit two variables like that and you check the correlation and the correlation appears to be somewhat related, then your next step is to fit a model to that and see if the coefficient for the model is statistically significant. Basically, it's a hypothesis test, and there'll be a p-value on any type of output you use on the row that correlates to that coefficient that goes with that variable. So you could use temperature. You would look at whatever row had your temperature on it, on your output, and there'll be a p-value that comes at the end of that, and that says that your coefficient is statistically different than 0.
Okay. Yeah, the R value was like negative 0.14. So
yeah, then it honestly, at that point, it probably would have a high p-value there, meaning that it's not statistically significant, or it's not statistically significant, meaning that it's not different enough from 0 for you to really need it to predict someone's happiness level.
Gotcha. Yeah. Okay. I yield the floor.
I have a question about.
Oh, sorry. Go ahead. Are you sure? Okay. I was curious if there's no correlation between our variables or no interesting results from an analysis you spend a lot of time on or that people are expecting. What's the best way to handle that situation? Does that make sense?
Yeah, I totally understand what you're saying. I've been there. In the words of the Big Bang Theory, no statistically significant results are still results.
Okay.
You just may have discovered that there's not a relationship that you were expecting to see. And one thing you may want to consider at that point is there some sort of lurking variable that might actually be going on in the background where we would expect to see that relationship that we're not seeing it? Is there a variable that I didn't consider that maybe I should have?
Okay, that makes sense.
But, there's times, especially in business, where somebody's going to say like, we expect to see these two things related. Show us that that's the case. And you have to go, no, I'm sorry. It's really not that way. I mean, you just, so my biggest thing, especially with the world we live in now, is I make all my decisions based on the data. And if the data doesn't support that, then you just have to kind of be blunt about it and show your support for it. So print the results, show that the relationship doesn't exist, and just be honest about it. Like, never try to tweak your numbers to go along with what your boss wants. That's the best advice I can give you.
Yeah, that makes sense. Thank you for that.
You're welcome.
And
Go ahead,
I was
Laura.
going to ask about the kind of data that you work with. Is
Okay.
it all data that your organization is collecting, or do you ever have to go out and find?
Most of the
Data
data I use is actually stuff that I found from different studies. I very rarely work with anything that I've actually collected myself, because most of what I deal with, because I'm more of a statistician than a data scientist, there's kind of a separation. I've never worked in industry, so I've been on the academic side. So a lot of what I do is like developing a method and then testing it. So we work with data that pre-exists. So I've worked with some different business data. A lot of what I work with is medical. So like I said, I've dealt with breast cancer data. There's a lot of that exists historically online. And one of the good things about that is in those cases, when you're trying to test a new method, you already know what the result should be. So you're testing your method to make sure you come up with the result, and you're trying to make sure you come up with that result stronger than the person before you. So, but I have worked with data that's been collected. Like, I've been recently working on a project with the nursing school. So I'm working with data that they've actually collected, and I'm doing the stats for them. So it's very rarely things that I collect on my own. But a lot of times I work with other people who have either collected the data or data that pre-exists historically.
A follow-up question is, like, are there any methods that you use to reduce like bias, or is that already hidden in the data? Like, when you get the data.
A lot of the bias that you see comes from the experimental design. So you've got to think about that. But if you're collecting your own data, you want to think about that beforehand. So like selection bias. I don't want to, if I'm wanting to get an estimate for the entire US population, I don't want to only sample people from Arkansas. Then the only conclusion I can come to is people from Arkansas. I can't come to a conclusion for the entire United States population. Or I can't only ask people in the top 1% of earning, because that doesn't represent the other 99%. So you have to kind of work that in, especially a lot of people do survey data. So you want to make sure that you're not introducing bias in the way you ask a question. So a lot of that comes from the upfront work. If you're going to do anything like that, it comes in the data collection. If it's pre-existing data that you're like testing something out on, or you're seeing like if your method works, most of the time you can read on how that data was collected, and the data sets that are used historically are really well taken data, so you don't have to really worry about that issue. But when you take your own, you've got to be really careful with the design of the features in that data set to make sure that you're not introducing anything. And if you possibly are, just be aware of it.
Awesome.
How you feeling, Whitney? You doing okay?
I'm okay. I'm about to have to shift. I may actually see if it'll finally let me log into my other computer. But I'm good right now. I was about to have to do the baby shift. Together ants all day long.
Anybody else got one? I've got one. Whitney, we talk about a lot of these tests kind of require the data to be normally distributed, and we went over kind of what that looks like. A histogram of normal data and some of the descriptive summary statistics. But is there a checklist of which measures would say this data is normal versus looking at it with a histogram?
The best way to check to see if data is normal is to use a normal quantile plot or a QQ plot. So a QQ plot, actually, I can show you. Give me just a second. I'll show you what it
I was
looks
going to say, what'd you call it? A normal quantile?
It's either listed as a normal quantile plot or a QQ plot. So what it does is it takes and plots on one axis. It is going to plot the normal quantiles, and on the other axis, it's going to plot the quantiles of your data. And basically, if your data is normal, those two things should match up. So you're going to get a straight line with a slope of 1.
Okay.
So it's really just a judgment call. You look at that graph and go, it looks straight from the bottom left to the top right, or close enough. And it's a really good way. It's the easiest way to check normality. And that's actually how we teach checking normality.
Okay. What about a box plot?
I'll show you what one looks like.
Okay, cool.
And, it says screen sharing is disabled.
Oh, hang on. I think I got to make you the host. Hang on just a sec. Participants.
Hold up, my other computer's logging in now.
What should I hold
Do
up?
that one and I'll close this one.
Oh, I see you coming. Yeah, there you So now make this person host. Where'd you go? There she is. Can you hear me okay, Whitney? There you are. Make a host, I believe.
I can hear you. It's not, there it goes. There's my video. Okay. Y'all get to see my cool UCA background now. All right.
So I just changed the host to you.
Okay. Let me pull that back up on this computer. But this way I can see y'all and I can see what I'm doing. I love my double screens. It's hard to function when I don't have them. Okay. All right, so let's see. Can y'all see that?
Yes.
Okay, let me zoom in on this a little bit. So these are some examples of what a normal quantile plot looks like. So here, and one reason I pulled this version up, like this is just me Googling and finding like a good example. Since y'all already talked about histograms, this puts the histogram side by side with what the normal quantile plot would look like. Sometimes like there's some judgment calls in a histogram. It's harder to say, okay, is it skewed? Is it not? The normal quantile plot is pretty straightforward because you're just looking for a straight line in those dots. So on here, it says theoretical quantiles on this horizontal axis. Those would be the quantiles if it was perfectly normal. And if it was perfectly normal, then those should exactly match up with the sample quantiles from your data. Or when we say quantiles, we mean like percentiles. So we're checking it against a normal distribution. So if it was exactly normal, those would be equal and it would follow that straight line that goes left to right. So notice here, it's not perfect because it's data, but we're seeing that it's pretty much following that straight line. So this is normal data.
What does a box plot, I see there's a box plot over a histogram. What does the box plot not tell you?
The box plot, so you can estimate if something's normal with a box plot. What this is showing you is that there are a few outliers in this data. That's the big thing that the box plot shows you that the histogram doesn't. But it doesn't give you the overall shape quite as well. If data is normal with a box plot, you should have the two pieces of the box are about the same length, and the two tails or the two whiskers are about the same length.
Okay.
Now you notice in this data, especially you can see like this is what's going on here. So the histogram, like it's really jumbled up within 3 bars. This is one place the box plot is pretty useful. The left side of the box or the second the second quarter of the data is really wide, that third quarter of the data is really, really narrow. So this is really skewed out to the right, and we see that we've got some outliers out here, and you can see those in that box plot. Well, when you look at the normal quantile plot, it should follow this line if it was perfect, and instead we're seeing this pattern that's way off. We're seeing like this S-curve, and so this data would be non-normal. But I can see this really, even this histogram with only 3 bars, it actually kind of looks symmetric if I don't see all those data points, because they're all like scattered out over here and they're basically 0. It's hard to see that. The normal quantile plot shows that very quickly. Where I've got all these large values over here, these large quantiles that I'm not seeing over here because the bars are basically 0. And then here's something that's even worse skewed, and you can see that it trails off in one direction. It's not, and you even got a point way up here. Very quick and easy way to check your data. And as long as you've got a column of data, pretty much any program is going to be able to do this. This is an example of doing this in Google Sheets. So.
Wow, Google Sheets.
Mm-hmm.
Wow, which is Excel light, really. I mean,
yeah,
pretty cool.
Yeah, so I mean, this is an example of what kind of output you can get from a basic program. So.
All right. Who's next?
I do have a follow-up on what you were just showing. So like talking about using Google Sheets, like what kinds of tools do you use for your data analysis? What kind of programs do you find most helpful?
It really depends on where you work, on what they're going to want you to use. My specialty is in R programming, but that's more of a statistician thing than a data scientist thing. Data scientists are moving more towards Python. I will say I have my grad students who now have discovered they hate Python because it's very picky with how you tab things. But those are more like programming language versions. Companies that aren't so heavy on the programming, a lot of times will use things like Excel or SPSS because it's more graphical user interface. As long as you find something that works, it's really up to you. Most things, especially in basic data analysis, are really reliable. It's when you start trying to do like really, really difficult things that it gets more complicated, and you kind of pick a specific program. Like our industry friends at First Orion, one thing that they have said to us is that they prefer R for most things unless it comes to machine learning and data mining. And in those two worlds, they use Python because it's really, really fast. Because they're solving problems with big data, and it handles those problems at a much faster computer speed. If you're doing basic analysis, everything's going to give you basically the same output. So it's just the way in which it's presented and how you like to get to it. I'm always going to program everything because that's what I know. But with my students, I always teach them something that's in some sort of Excel looking format, which would be like your SPSS, your Excel. And then they also use a program that's done by Pearson called StatCrunch. So it's whatever makes you comfortable, but you should get basically the same output, the same numbers with anything.
I'm curious, is there anything that you use to learn R, or do you just kind of learn it as you go, as you deal with certain problems?
I would suggest, if you want to use R, learning some basics of the language, which I'll give him my intro to R workshop sheet. So if you want to go through that, that's a great place to start. There are several tools online that will teach you, especially if you're willing to like pay $10 a month to learn. I've actually done that for Python myself because I wasn't a trained Python programmer. So I like DataCamp. That's a great one because it checks you as you go with every single step. And they have classes for R as well. One thing I will say is if you're going to try to do any type of analysis with R, make sure you look into the tidyverse. because like TIDY, like tidy your house. It's all about how to clean your
Okay.
data up and make it look nice and pretty and easy to work with. And that's actually, I've spent a whole semester last semester teaching my grad students about the tidyverse and its intricacies, because you can pick little pieces of things out of your data so much quicker than you can using the base R stuff. So I say like take an intro into like what R actually is and how some of the basics of the language work, like the fact that it's a functional programming language. And then from there, learn some of the packages and don't just rely on base R, because if you go to like a traditional old school textbook and just try to like read it through, they're going to do all the base stuff. And then you're going to learn like 2 years later that there was an easier way to do it.
I got you. I'm using R now, but I haven't used the tidyverse package yet.
So
R
the
is what we use
tidyverse
mostly for my
combines
job.
some packages. It combines ggplot2, dplyr, forcats, and I can't remember what the other, it's like 4 or 5 packages that are together. dplyr is like my bread and butter. That's where I live.
I think I used that one. Yeah.
So it's
Okay.
part of the tidyverse, but they're all packages that were developed by the same author. So they're all packages developed by Hadley Wickham. And I can always say all hail Hadley Wickham. He's the king of R in my opinion. He's the guy who works for RStudio and like his job is just setting there developing packages. And he tries really hard to make everything super user friendly. And that's why ggplot2 graphs are so much prettier than base R graphs. So especially if you're doing a lot of graphics, the tidyverse is where it's at. Learn ggplot2. It takes more time up front to learn, but it's much more intuitive in the way you program the graphics.
Okay, that makes sense. Thank you.
Anybody else?
Yeah, what's the central limit theorem?
What's the central limit theorem? Okay, so with this idea of sampling distribution, so when I'm going to, let's say I'm dealing with a population that has a set mean, right? We know the mean is a parameter, it's fixed, we just don't always know what that number is, which is why we're trying to estimate it. So we take data, right? We get samples of data, and from those, like we were talking about earlier, we can get a whole bunch of different possible answers when we take our sample data, right? If my mean is 50, I could get a sample mean of 49 or one of 56 or one of 34. And we can look at how those are all possibly laid out, right? Well, what the central limit theorem tells us is that if I look at all possible sample means, as long as my sample size is big enough, that distribution is going to end up looking like a normal curve. And then I could calculate probabilities about those sample means. So, and the sample size actually plays into how widespread those are. So we were talking, when John said earlier that the bigger the sample size you take, the more accurate your answer is. What that's actually talking about is how wide the distribution of that normal is. Is the standard deviation bigger because your sample size was small? Or if your sample size gets larger, that standard deviation is going to get smaller and it's going to become a more peaked normal curve, centered right at the parameter you're trying to estimate. So the central limit theorem allows us to find that parameter with a really high probability.
Okay, thank you.
So I may actually, let me see if I can get this to come up. I may actually have a little like simulation applet that I can show you that would visualize that really, really quickly, if I can get it to come up. My computer appears to be wanting to work right now. We'll see. Sometimes the UCA network is great and sometimes it's awful. And now my login page is frozen. I'll come back to it if it loads. I'm trying to get this this little StatCrunch applet to open. I may be able to get to it through the Solely Stats page. Stats, resources. Nope, it's not coming up there. It's weird that it's not letting me log in. This looks more like it's their website and not my computer. I'll go into it through a different way. I've got like 3 ways to get to it. So. But that's one cool thing. Like if you ever have a theorem like that you're like asking questions about, a lot of times there's visualizations of how they simulate that so they can show it to you visually online. Even if it's just like a YouTube video or somebody actually walks through the simulation. And honestly, simulations are one of the best ways to really visualize a theory. So anytime there's anything like that, like on your own, if you're like, okay, I don't really understand what's going on here, look at a simulation of that situation, even if it's just like coin flipping to see like how things turn out. It makes a lot of sense visually. Let's see. I think I'm going to get it open this way. It looks like it. Come on. This way just takes a lot more clicking. Okay. Applets. Okay, let me share my screen again, and then you can see what's going on over here. Okay. So in this scenario, what we're seeing is like, say this is my parent population's probability distribution. This one's uniform. It's perfectly flat. It's nowhere near normal, right? Well, what the central limit theorem tells us is that no matter what this shape is, as long as my sample size is big enough, the sample means will follow a normal curve. So what I can do is I can take samples of, in this case, let me look at samples of, this one says size 2. So if I take 1,000 samples of size 2, this one just represents the last sample, and this shows what those 1,000 samples would look like as a histogram. Again, it's not perfect because it's random, right? But it is symmetric and bell-shaped, even at a sample size of 2. And the higher the sample size gets, the better that curve is going to look. And we'll also notice the narrower it's going to get. The standard deviation is going to go down. So you'll see that the mean is essentially the same as it is up here. And the standard deviation, notice, the standard deviation will always be smaller than the standard deviation from the population. And the bigger the sample size gets, the narrower that standard deviation is going to, or that width is going to get. So the standard deviation is going to go down. So let's look at samples of size 25 instead. So here's my last 25. Notice now I've got this symmetric looking curve, but it's much more narrow. Before it went from basically 0 to 50. Now it looks like we're going from about 15 to 35. The mean is still about 25, but the standard deviation went from 14.4 to 2.8. So no matter the fact that this started out as a uniform didn't affect this normal shape. And this works even if the parent distribution is skewed. So let's say I had data, I'm going to make that data look really, really skewed. Okay, high probability over here, and let's actually taper that off a little bit. There we go. Okay, so I've got this skewed distribution that I've just randomly created. So if I take really small sample sizes, notice that my sample means look skewed too, right? So this is where I said the central limit theorem says if the sample size is big enough, this down here is going to look normal. The mean is still about the same. The standard deviation has gone down, but the shape is still skewed to the right. So if I up this, let's say to 15. Oh, didn't mean to do that. There we go. Okay. And I take another 1,000 samples. Notice it's much more normal that now that the sample size has gone up, but it's still skewed somewhat, right? We still got a little bit of a tail going on over here. If I increase that to say 30, notice now it looks very symmetric and bell-shaped. It looks like a normal curve. Mean is still about the same as it was originally. Standard deviation is quite a bit smaller. And the central limit theorem also gives you the formula for exactly what this number should be based on this number and the sample size.
I just had a light bulb moment. I don't know if everybody else was in the dark until just about 10 seconds ago, but it's occurring to me this is pulling 30 out of a population 1,000 times and looking at the results of that.
Yeah, so this is
that
just one
sample
sample of
30.
size 30. This is 1,000 samples of size 30. And in the each number here, so this is every individual from that last sample. This is the sample mean of a sample of size 30 1,000 times.
Yeah, no matter how skewed the data might be, if you take enough numbers of samples.
Well, it's more about the sample size itself. I could have only done this. Let's say I do this. You have to take enough to be able to see the curve. Yeah. So the goal is about the in theoretical curve, but it's the sample size itself that's what's causing the curve to look that way. Dang it, I bumped the wrong spot. So let me do this.
Yeah, I'm just remembering from.
There's 155. Even at that point, we're already starting to see that normal curve, right?
Yeah.
I just click 1,000 because it happens like that. Because the central limit theorem is about what the overall curve looks like when you take an infinite number of samples. But we know we're not going to do that in the real world. But the shape is already determined as soon as we pick the sample size.
Yeah, I'm just flashing back to my stats professor saying that. I can literally see him standing in the room saying that no matter how the data is distributed, the original data, the population is distributed. If you take enough samples, the mean of the samples will be normally distributed.
Right. If the sample size from those samples is big enough.
Yeah, there you go.
So, and like I could draw this and I can make this like multimodal where it looks like a roller coaster and it's still going to hold.
There you go.
The shape doesn't matter. That's the central limit theorem.
Thank you.
I hope that answers your question. I may have went a little overboard, but I hope that answers your question. And
that is web-based, that statcrunch.com?
This is StatCrunch. So this is included with any Pearson textbook. This is what I use to do simulations with my students in class. So I knew the applet already existed. Some of these you can actually get access to the applets through the book authors. So I don't know. There are some that are available from our book's author, but I couldn't figure out where they were. I go through them most of the time just straight through the website. So I couldn't get it to, couldn't locate it from his stuff, but I know it's on here somewhere. Let's see, data, videos. I'm not seeing his applet page because he's just redone his website. So if I can find it, I'll let you know, but you can access some of the applets without having to have access to the web page. But it's a little harder to do.
Okay, we're coming up on our hour. Anybody else? I got a real quick and easy one. Whitney, when to use, when you're looking at two continuous variables, two numerical variables, and you want to see how they're correlated, what's the difference between R and R squared?
So R is the correlation coefficient. It only tells you, it tells you strength and direction of only a linear relationship. So you can only use correlation coefficient or R if you're only looking at a straight line. Now you can calculate R squared for any regression model. And it tells you, what it actually tells you, it's bounded between 0 and 1 instead of -1 and 1. And it tells you the amount or proportion of the variability that your model accounts for, no matter what type of model it is. That model can be exponential, it can be quadratic, it can be linear. It works on everything with the way that it's calculated, but it tells you the strength of the relationship in your model, or more specifically, how much of the changes away from the line your model is accounting for. So
Okay.
if everything's close to 1, everything's going to be really close to the line. If there's more variability going on, like, so we're saying variability in Y, that's okay. I'm looking at only how the Y's are changing, right? They're going up, they're going down, they're curving. Well, if my model's accounting for a lot of that curvature, then my R squared is going to be really high. It's going to be close to 1. If I'm not accounting for those changes in the Y values, meaning that my Y's are bouncing, or things are bouncing really far away from the line, then my R is going to be smaller or closer to 0.
All right.
It's basically how much error in the Y did you account for with the model, or how much is X explaining?
Okay. I'm gonna go play with that with a couple of different shapes. Linear is pretty easy.
Just remember, correlation only works if it's a straight line.
Yep.
That's the big thing.
Okay. Anyone else going once, twice? All right. Well, Whitney, thank you so much for coming in and putting a good air of credibility on our statistical discussion. And I'll post. I've got your R workshop, which I'll post in our classroom from last time. But those 3 files, the PDFs for your inference, probability, and the R workshop, those would be great. I'll post those too.
Yeah, I'll get those to you. I've got the file. I went ahead and opened the folder up right now so that I can send those over.
Okay. All right. Well, with no further questions, I think we should go on break and come back at 10:15, 15 minutes after 10 on cell phone time. And thank you so much, Whitney.
It's good to see y'all.
Thanks a
Good
lot.
to see you,
Thank
Chase.
you.
Okay. Hey, happy reunion. All right. See you guys in about 15 minutes then.
And if y'all just FYI, if y'all have any questions, feel free to send them to my UCA email. I mean, I'm kind of slow with responses right now because I'm also trying to get ready for baby. But if you need anything, y'all feel free to contact me. Like our webpage is uca.edu/math, and I'm on the faculty page. I'm at the very bottom. You got to roll all the way down to the W's. So
Okay.
it's really easy to find me.
Thank you.
All right. Thanks, Whitney. I'm going to pause recording and I'll see you guys back at 15 after 10. Okay, and we're back. And I have resumed resume recording. Okay, guys, I want to knock out this this Excel U.S. states exercise. So I'm going to give you the rest of the day to finish that. Okay. Like I said, couple I haven't seen any upload at all, which has me scared. So everybody's got my cell phone, right? So text me or call me, your choice. If what I'm looking for isn't clear, or if you need help, deciding on something or doing something, and I'll run over to my computer and help with the Googling, and we can jump back into this video classroom if necessary. So I'm creating the assignment now. I'm making the instructions as clear as I can in the description, but I'm looking for 2 files that look just like mine, which let me share my Chrome. So I'm typing that up, but can I save what I've typed? Save. It's not ready yet. It's not published yet. That'll be the assignment. Let me go back to my dashboard and my class. Okay, down here in data analysis with Excel, I'm looking for my dog to stop barking. I'm looking for your version. Basically, I've got a couple of extra tabs in there, which is okay, but I'm writing up in the instructions. I'm really looking for 3 tabs. Your clean worksheet with your columns that you're working with. Another worksheet with your charts on your chart or charts on it, and then trying to use that tool pack to run some numbers on it. And I understand if you're on a Mac and you can't, and we'll figure something out. But turn in your version of my my V2 happiness states project there, and turn in your version of the PowerPoint, the PPTX file that I've uploaded there. Quick, easy. Don't put too much, thought or freaking out about whether you got to an accurate null or alternative hypothesis, that sort of stuff, because we'll go over it in class. We're each going to bring up, just like I did this morning, we're going to bring up what you've accomplished, like Tuesday and Thursday of next week, in between other things, because we do need to kind of put this aside and move on to SQL and more Python. So take the rest of the day of your time here. Hopefully, don't let them know that you're not in class, or that I'm not talking. And finish that off, and you'll see an assignment down here that's like final states workbook or whatever. You'll see it's a different assignment. So upload it there. It'll say final U.S. states project, something to that effect. Okay. I thought Dr. Worley did really good. That was cool, Chase, seeing you reunite with a college buddy out of nowhere.
Yeah, it was crazy. I recognized the voice, but I didn't put 2 and 2 together until she said, "Hey." I was like,
Did you realize she'd gone on and gotten her PhD and all of that stuff, or
I had known, I'd known she had been in Texas for a while, but
yeah,
that was cool. So
yeah, there you go. Arkansas is a small town. Okay, guys. Like I said, holler if you need me, but let's put this project to rest. So please get those turned in today before you do anything with work. Use the next 2 hours to finish up your worksheets and prepare that presentation. And holler if you need me, and otherwise I'll see you Tuesday morning at 8:30.
Thank you. See ya.
Okay.
Thanks, John. Bye, everyone.
Bye.
Good day.
Have a good day.